Good. All right, so, wow, that's loud. All right, so this talk in 2014 I did Network Behavior Anomaly Detection, UBA or UBAD as it was then, UEBA now. So I took the same deck we started with in 2014 to talk about the benefits of NBAD and UBA. In this talk, we're going to talk about how to break it, how to break NBAD, how to break UBA, and then how to mitigate against those attacks. So a little bit about me. I was active duty Navy from 1995 through 2005. I worked on Hornets for the beginning of that, forward deployed. 9/11 happened, went and spun up the network security group, got to be a founding member of the School of Root, so I've won DEF CON more than most human beings. And then left, did consulting work for DoD State Department, also did product testing for InfoWorld magazine for a number of years until that closed and journalism died. I went to work for Landcope, which is where I first spoke here at Converge in the first years of Converge, and then left after the acquisition by Cisco to form WITFU. What we're going to hit on today is how does NBAD work, how does UBA work very quickly, the relationship between data poisoning, baseline poisoning, non-repudiation, how to protect against those things. We're going to go into some specific attack scenarios and tactics, and then we'll open up to QA. This deck is up on Twitter, so I'm at Charles Herring, or if you go to charlesherring.com, I'll take you to my LinkedIn page. You can download the deck. It has the code in it for the exploits. Real quick on how we detect things in cybersecurity. Signature-based detection is when you inspect the object for a known pattern. There's an indicator compromise referenced. In the food world, it would be like looking at your food and there's mold on it. So you know what to look for, you found it, there's a pattern match, and you trigger on it. Behavioral-based detection is when you look at the actions of the referenced entities. A host is doing something that's known bad, and you trigger on it, or a user is doing something that's a known bad behavior, even though you don't necessarily know why or what the campaign is. And anomaly-based detection is a deviation from normal. You do machine learning, that's how we define it today, that comes in, you look at patterns, you assign a reason for that pattern. Could be network scanning, could be benign, could be nefarious. But essentially all of this was taken from a 1986 paper written by Dr. Dorothy Denning at the War College, and it really hasn't changed that much. Marketing's messed with some of the words, but these are the three detection methods we'll look at today. Known exploits are best caught by signature detection. If you know what the hash is and the hash is matched, you know what it is, you know what the exploit is. Very high fidelity in detecting known exploits. ODA, or not yet known exploits, are best detected by behaviorals, in that the way that you're doing an exploit is the same, but the payload or the subsequent behavior that comes after the exploit is the same, right? They're going to encrypt your disk, or they're going to delete files, or they're going to exfiltrate data, or something along the attack continuum. When you're looking for anomaly detection, you're talking about pattern changes, that something normally happens. A user normally shows up at a certain time, logs in at a certain time from a certain location, and then deviations from those known patterns can tell you when human beings are acting differently, which can be an indication of credential abuse or insider attack. When in doing anomaly-based detection, you have to build baselines, or another way of saying that is the baseline is the calculation of normal. What is the normal time a user or a set of users should be logging in? And it takes time to build these. The longer the baseline exists, the more reliable the baseline is. Supervised machine learning is looking at very specific data points and building metrics on those data points over time. Unsupervised machine learning is looking at all permutations and permeations of data to look for new things and new different calculations that we didn't know before. Network behavioral anomaly detection came around in 2002 was the first time we started talking about that. It generally works off of metadata because it's only building patterns. You only need to know how many bytes are exchanged, and so you can do most of that inside of the TCP header space. And the advent of NetFlow, IPFix, CFlow, JFlow, all these are records that represent communications from route switch infrastructure became a really good place for this. And it allowed visibility on horizontal communications or east-west communications inside the network. They're quantity specific, so how many packets, how many bytes, those types of things. It doesn't really matter what's inside of the packet. It doesn't matter that there's an exploit inside of the payload. It matters how many payloads are occurring. If you want to look at the pattern itself, that would be signature-based detection. Sometimes you hear NBAD referred to as NetFlow security tools. This is a list compiled by Gartner of different tools that do this. Mine's the bottom one. I used to sell Cisco StealthWatch at the top. When you're looking for what type of anomalies are in the wild right now inside of NBAD programs, you're looking for service traffic threshold anomalies, how much web traffic is being exchanged between the internet and the web servers, how much data is accessed from the internal data stores, those types of things. Same thing with service. Geographic traffic anomaly is we normally only get 100K of traffic to Tehran or some other geographic region in a period, and now we have 3 times standard deviation of that traffic, so there's an anomaly, and where in the world we're receiving traffic. Data hoarding or data staging is a host or a group of hosts. How much data do they consume from the internal network in a given period, normally a day? Data disclosure or exfiltration is how much does a host normally send out of the network to the internet in a given day. So those are very common types of baselines to build and detection that goes inside of anomaly detection. UBA is an extension of it. It used to be called UBAD. There was a division between network behavioral anomaly detection and user behavioral anomaly detection. And now it's all really wrapped into user entity behavioral analytics. But it just looks at, beyond looking at IP addresses and hosts, you're now looking at the access of users to files, host to host, host to user, host to files. This is a list compiled by Security Planet on stuff that's currently doing UBA today. This was last year's paper. Things you're looking for there are like magic carpet attacks, someone logging in from China when they've never logged in from China before, or they're logged in from China and now they're logged in from the Detroit office. So how do they move that fast physically across the globe? Time of day, users that log in at 8 o'clock in the morning from 8 to 10 every morning, and now they're logging in at 3 o'clock in the morning on a Saturday, presents a potential type of anomaly that needs to be addressed. Which host are users accessing? If a host logs on the network and they're only hitting SharePoint and they're only hitting the internet, why are they now accessing route switch infrastructure or something along those lines? What type of data are they accessing? When you look at user to file level access, who's hitting the information that holds PII or source code or something along those lines? Who is accessing it and how? And as also service access. If maybe they only hit email, LDAP, web services, and now they're starting to log into SSH or something else that's outside the pattern of a given user or set of users. So what we're going to look at today is data poisoning. Whether most of these features with NBAD and UEBA are not standalone products in general anymore. They are features of what we've called SIM, security incident event management tools over the years. But there are a handful of standalone products. Things we're going to look at is mass implication. So what that generally means is my host or my user is doing something nefarious, but then I generate data that says everybody's doing that thing. So you can't pin it on me because it looks like every single user or every single host is doing that, so you can't isolate the data. So it poisons the usefulness of the data in the system. Baseline boiling is, in anomaly detection, you're looking for an exceeding a defined baseline. So when you boil the baseline is you expand the baseline over a period of time so that when you want to trigger the exploit, the baseline is now grown to a place that will allow you to get away with it. And so that may be data staging, where every day you're collecting a little bit more data from a set of hosts. And then when you're ready, you're finally ready to extract the real data you have the flexibility in the baseline. Attack masking is when you're doing one type of attack, but then you generate fake records that make it look like something else, that makes the responder unable to determine which is which. The ways of achieving these in this system that I'm going to show today are log spoofing, so just different methods of generating fake records that poison the data to accomplish these attack types, or behavioral spoofing, to where the things that are generating logs are tricked into thinking that you're performing the bad behavior. A couple places for generating traffic. It's either on a machine, a VM container, so something you own inside the network, or tricking a networking device into doing this for you. As far as mitigation, we're really talking about non-repudiation. And we have some hardcore challenges in data collection. We're still doing most of our data collection in cybersecurity over UDP. And so there's no checking of validity of that data. We can ship, many technologies ship logs over TLS using client-based authentication. There's a lot of challenges with this. One, you have to maintain a PKI infrastructure to include revocation list, or doing that through OCSP. It also has the potential of breaking the network because TCP has the downside of having a handshake, and so if the host that's supposed to be collecting the data goes down, there can be a negative impact on the network. Some route switches do reverse path verification to deal with IP spoofing, so you'll see I'll do a good bit of IP spoofing here in a second. And so some of the devices, this is the command from Cisco to enable on the interfaces to verify that the host that's saying it is a certain IP address is actually on that network. Another way of dealing with it is putting data, your telemetry that's used in evidence collection, in a segmented part of the network, either through microsegmentation or through Cisco offers TrustSec for this frame modification for validating delivery of data. Honeypots are another good way, because honeypots, and there's commercial deception technology like TrapX is a good example of this, where you spin up trip wires throughout the network that have no valid purpose. And if something scans that machine, you know that it's being scanned, because nothing should be communicating to a non-existent host. And if it does something, if it sends an exploit to that honeypot, there's a no false positive situation in honeypot, so they can help figure out when data's been poisoned, what host and what user was the actual culprit. As data is being ingested into solutions like Splunk or QRadar, Logarithm, or product iPedal, you want to tag how you got the information. Did it come in via UDP? Did it come in via TLS? So that if you run into a data poisoning scenario, you're able to filter out the stuff that you cannot be sure was delivered correctly, and then work only off the data that has a strong non-repudiation. Another way of dealing with it is putting in secure visibility frameworks. So Gigamon's a good example of this. You tap your infrastructure, and then they create metadata directly off of the tapped network traffic. And so in that way, none of these attacks would work in this scenario, because it's working off of mirrored or tapped traffic. So as far as the attacks we're looking at today, they're applicable through the attack continuum outside of initial access. All of these require a machine inside of the network to do these attacks. They don't necessarily have to be privileged machines. Some of these attacks will work on wireless network, guest network, and that type of thing. So the first technique is a pump and dump scenario. So you bring up normally a VM or a Docker container, and you assign a MAC address to it. You assign an IP address to the machine, and then you do something. Maybe you're doing recon, looking for SQL servers, but you do something. The machine is going to get reported, but then you kill that container, spin up with a new MAC address, spin up with a new IP address, and now the machine that they're looking for has disappeared off the network. So one way that the only real mitigation against this is if you're doing logging at the access layer, so the access switch or the access point for wireless is logging the MAC address and other characteristics of the host. So this is really simple to do. If you install Docker on any host, the first command I have here creates a new network. So actually, this should be Docker create. No, this is creating a host. So it creates a host on the network of the host. So whatever machine you're on, it physically binds to the network card. That's what network host is. The driver is the host machine. You establish what the MAC address is for this Docker container. The next part is telling you which Docker image to use. So that would download the newest release of Kali Linux. And this could be anything. You don't have to use Kali. You could use any flavor of Docker you wanted. It could come from your own repository, and then it just gives it the name of Kali 1. And then you start it and execute. You can do stuff, stop it, and then just rerun that first command. So you can swap out your MAC address, swap out your IP address, and this is a common tactic we'll use on additional attack scenarios going forward. This one's really cool in a day of containerization, is you can do what I call a pocket dimension. So on a single machine, you create a network that can be a /0, it can be the whole world as a network, but it's bound to the network card. So if you're connected to an access point or to an access layer switch, it's going to see the traffic as if it's happening on the switch. But you spin up one host, for instance, that may be on the internet. So give it a 4.4.4.4 address, and you have a 10. An RFC 1918 address internally, and you're communicating on this fake network. And what that's doing is it's generating records in different scenarios that look like external traffic is happening around the world or inside of the network, but it's really not happening at all. It's happening on your single machine, but the telemetry about those metrics are being generated inside of this pocket dimension. And setting that up is pretty easy. You use Docker network create, and on network create, you define the principles of the network. What subnet is it on? What is it bound to? And then you have essentially a virtual network there. It can be a /1, a /2, a /4. You can create multiple networks for different subnets, but you essentially build networks using IP space that is routable on the internet, so that you can perform attacks that should not be observable. So the next thing, I'll create a Docker network called Pocket, and then spin up a Docker container called Kali 1, and assign it an IP address of 4.2.3.1. And you can also, in this scenario, assign the MAC addresses as well, as we did earlier. Then I have another host in that Pocket domain called 10.10.10.1. And then I start both of those containers. And as you're doing the work inside of that Pocket domain, it will generate metrics depending on how the telemetry is set up. We'll look at some ways of doing that in a second, that look like things are happening that are not really happening. So you can make it look like China's attacking your network when China's doing nothing, right? You take a GeoIP address, you assign it to one of the containers on the Pocket dimension, and then you've set up a test bed for generating telemetry to confuse logging solutions. Another technique that we can use is log spoofing, which is communicating directly to the logging source. The challenge with this is you have to find the collector. So the thing that's listening for Syslog, or the thing that's listening for NetFlow or API calls, the thing that ingests data. So you can do traditional recon stuff like DNS zone transfer type of dumps, looking for how information is being gathered. You can just do a send scan for Syslog running on 514 TCP to look for those sources. Of course, that's going to be noisy, so if you're going to do that, do a pump and dump. And then you essentially just send it artificial records that will accomplish what you want it to accomplish. Authentication successful, different, whatever we're going to do. Of course, ACLs are important here, going back to not allowing any guest network machine to get to your logging server would be a great way of doing this, and then not disclosing where those things are on the network through obfuscation is another approach. This is a very simple way to spoof a syslog message. So essentially you echo a message to Netcat, and you point it to the place you want it to go to. It looks exactly like a server log. Anything in UDP Syslog can be generated this way. You can do CEF messages. So the stuff in the quotation marks is the Syslog message that's going into the Syslog collector. So very simple approach using Netcat. There's an open source project called Samplicator, and that's the link on GitHub to get it. It opens up a port or multiple ports. You put in rules, and you can send UDP packets to multiple destinations, and it will maintain the original IP header. And so where this is helpful is you can have it send it everywhere. So you send one packet into Samplicator, and it can potentially send out to thousands of different sources, hoping that one of them is your log collection source. This only works with UDP, but it works with UDP over Syslog over UP, NetFlow, IPFix, SNMP, all of that. TLS is a little bit more complicated, but you can still get data into a TLS listener because even when TLS is used, it's typically not doing authentication. It's not authenticating the client certificate. If it is, then you would need to add the client certificate here, but this is just some shorthand. This is functional Python code. You create a socket. You're using TLS v1. You're not verifying the server certificate because we don't care in this scenario. You open up the socket to 10.10.10.1 on 514 or wherever it is, and then the write command is the message that's being transmitted over TLS to the logging server. If you have API-based collection, like Elasticsearch uses REST API, Splunk uses REST API, so if you find the locations of these and you want to post in, it's just an XPost command. The -K is just to disable certificate verification, and you just post the JSON object of the message that you want to go into the system. So that's curl. NetFlow is a little trickier just because of the nature of NetFlow, but if you spin up a pocket dimension, you download nprobe, and you run nprobe on one of the NICs inside of the pocket dimension, it's going to sniff the traffic going in your little imaginary network, and it's going to generate NetFlow records and send them to the place you want them to go to. So if you wanted to look like China was downloading all your data, picking on China again, you create a host in the pocket domain, have it download data from another imaginary machine. It's going to generate the NetFlow records and then forward those on to the NetFlow collector. So the nprobe command is just what interface am I sniffing on, and then where is the collector and what port is the collector on, and it will send the packets directly into that collector to poison that data. So taking that into account, doing an NBAD mass implication on a network scan. So let's say you have a real host, you want it to scan the network, but you want to cover up the tracks by saying everything is scanning the network. So as the responders are looking to come after your host or kick it off the network or find you, they have to go through every fake host that you also generate records on. So the quickest way to do it is to spin up a pocket domain, have multiple scanning machines with different IP addresses across different domains, use nprobe to send the NetFlow out of the pocket dimension to the NetFlow collector. So you're scanning all these fake addresses inside of the dimension as you're scanning the same addresses on the real network. And so you're generating real NetFlow records about what you're actually doing, but you're also creating NetFlow records about a whole bunch of fake accounts that are not being generated. And so as responders are coming in, they have to find all these fake machines and get them off of the network before they can find your machine. And really, IP spoofing is probably the only thing that's going to help you here, and also MAC address logging at the access layer on NetFlow. But this is, and then also tagging the data, going back and being able to filter out which data was collected from those NetFlow records. Another one is a NetFlow masking attack. So let's say you're doing a SYN scan. You have one machine doing a SYN scan, and then you're generating NetFlow records generating the SYN-ACKs. So the way a SYN scan generally gets detected inside of an NBAD solution is you see so many SYN packets going out to destinations with no return SYN-ACK. And so do the scan in the real world to discover a host, and then in the pocket dimension, generate NetFlow records that are just for syntax and send those directly to the flow collector. Or if the pocket dimension is running on an access layer switch, the access layer switch will generate the NetFlow records for you instead of you using nprobe to do it. So you're scanning in this fake world, a 3850 from Cisco or something else will generate NetFlow and automatically send it to the flow collector. And one way to use this would be a honeypot. So if someone's scanning and then you have a connection that it hit a fake address, that network connection inside the honeypot and the forensics coming out of that would help determine what the real attacker was from the fake. Baseline boiling, same types of techniques. It just takes a lot of time. So you basically, every day you increase the metric that you're generating either in the pocket domain or on the real network. So you can download a mega traffic on day one, then a mega and a half on day two. When you're dealing with different technologies, some of them build baselines on a per entity basis, so every host has its own baseline. Other technologies use set-based baseline, so all of the wireless hosts share a common baseline. So when you're boiling a set-based baseline, you need to have more participants in the boiling. But the idea there is if you need to do long-term systemic exfiltration or staging, you're going to want to boil the set metrics by spending 30 or 60 days slowly incrementing up the byte count. So download a meg, 2 megs, 5 megs, 10 megs until you get it up to the level you need for exfiltration. Alternatively, most baselines do not, or most counters for a given period do not exceed a 24-hour period. So if the baseline is 10 megs a day, you transfer 10 megs a day and do that every day, then the counter is going to reset at midnight, and then you've got another 10 megs for that day, and then another 10 megs. And these can also be used in combination with each other. So if you have the time to do a slow exfiltration, that's generally the best way to do it for avoiding anomaly-based detection. So with all those in mind, perfect. Setting up the architecture around TLS is really important. The problem with this is NetFlow doesn't support it even in the RFC. IPFix supports it in the RFC, but I've never seen a vendor create IPFix that supports TLS, though it is in RFC 5101. But using TLS where you can is important. You can also generate NetFlow off of a visibility fabric where you can control the flow of data. So Gigamon or another TAP technology that's inspecting the data, creating metadata off of the raw TAP is a way to get the data out into a different format, maybe a common event format over TLS for Syslog. And wherever you're using TLS, you want to make sure you have CRLs in place, IP spoofing as we already hit on, and then microsegmentation and ACL. So that is 30 minutes. Any questions? See you at the bar.